So we are going to work on Vivado 2014 today. We are going to create project with Vivado 2014 and we are going to download this code into the artix 7 FPGA. In this video, we are going to discuss initial steps, how to create a project, how to simulate, synthesis, constraint file writing, and then implementation on artix 7 board. So let us start with creating new project. First step is create new project. Next, go to next. Here you have to give the name of the project. While giving the name of the project, please take care that do not add any kind of spaces. Do not start the name of the project with the numbers. Do not use dot in the name. So these three cares we need to take. Go to next. Go to next. Now here we have selected RTL project tab. As we are going to use artix 7, our product category, let it be all. Family select as an artix 7. Subfamily will be artix 7. Package depends on the kit. So for our kit, we are using CSG 324. When we are going to download the program into the kit, we will show you the kit video of the kit as well. So at that time, this will get clear. Speed grade, right now you can select -1. After adding all this filter, our last IC, that is XC7A100 TCSG 324+1, this we are going to use. Go to next. We have to finish this. So now our project has been created. We need to give the inputs and output name, that is the ports name to our project. We need to create a Verilog file into this project. So for this, just make add sources. In this add sources, we have to select the option add or create design sources because right now we are writing Verilog file. So we will select add or create design sources. Go to next. Now we don't have Verilog file previously created. If the file is previously created, then you can add the file, otherwise create file. Give the file name. Same rules are applicable. Do not use space, dot, or do not start from the number 1. Make it okay. Select that file and go to finish. Here we have to give port name. So port name, give as an A, B, sum, and carry. As we are going to write this code for half adder, sum and carry will be our output port. A and B will be input ports. Sum and carry will be output. For half adder, sum and carry are output. So make it okay. We are not going to select bus over here because bus is used for the vector inclusion. So we are not using vector. We are working with the single bit. So bus we have not selected. Open your file by double clicking on your Verilog file. In front of you, Verilog file is open. This file is blank. Only input and outputs are declared. We need to write down the code. As this is first code, we are going to write the very simple statement. There are different types of modeling style in the Verilog, that is behavioral modeling style, structural modeling style, data flow modeling style. From that, here we are writing simple 2 statement. That is data flow modeling style we are going to use, and for sum and carry, we have written 2 statements separately. Our equation of the sum is A XOR B, and equation of the carry is A and B. Semicolon. We will save this file file. Once you save this file, we'll create test bench file to simulate this code. So again, make add source, add or create simulation sources. Go to next. Then again, we'll have to create file. Only the difference is this file name should be different than your module name. So here you can write as an half adder underscore TB. It will reflect test bench. Select that file and make it finish. There is no need to give any kind of input and output as it is test bench. So simply you can go to OK. In the small sources window, you can see that two files are there. One is your Verilog file, which is the file which we have written as a code. Another Verilog file will work as a test bench. So open that test bench file. This test bench is completely empty. Now, as test bench do not have any kind of inputs and outputs, so bracket start, bracket end and semicolon will keep as it is. Even that bracket you can remove, but still for a sake, as this is first program, we will keep that bracket as it is up till you do practice. We are going to reflect our input and output with the names resistors and wire. REG, inputs are reflected as in resistors, outputs are reflected as an wire. Significance of resistor wire will be explained separately into the theory lecture. After declaration of this inputs and output, we will call our module to be present into the test bench, because test bench is a code, is a Verilog code which we are going to write to provide stimulus to our main module. So how to call our main module into the test bench? Main module name, then space UUT, that is unit under test, into the bracket, port mapping we are going to do. How this port mapping will be done? Dot A into bracket A. What is the significance of this dot A and A? 1A represents the resistor which we have declared into the test bench. Another A is the input which we have selected in our main Verilog code. Very important point. Verilog is case sensitive. So whichever alphabet you will use as in capital, you will have to use the same word as in capital throughout the program, throughout the test bench. Otherwise, your port will not get recognized by the program. After calling our submodule, we will start to write the test bench with initial begin. Under the initial begin and end loop, we will write all possible inputs combination. This is the first test bench which you are writing. So we are writing a very simple way test bench. Ideal and industry test benches are not simple as you are observing right now. But as you are in learning phase, we are writing this test bench in very simple way, where you can see that we have actually modifying the inputs. That is A is equal to 0, B is equal to 0, delay is been provided. Now this delay, where is the unit of this delay? The unit of this delay is at the initial of the program, where you could see the time scale factor mentioned in the program as a first line. So that will represent the unit of the delay. Details will be explained into the theory wala part. We'll save this test bench. We'll save this test bench. If your test bench is completely okay, then you can observe into the sources window that your main module is inside the test bench. So there is a plus sign. If you will maximize that plus sign, then your main module will be inside the test bench. So this is the proper integration of your test bench and the main module. If any error is there, then it will show by red underline and it will show as a syntax error. So right now we don't have any kind of syntax error. we can synthesize this code. We can simulate this code. Before synthesizing, we will simulate this code for the simplicity, and then we'll go for the synthesis. So click on the run simulation, run behavioral simulation for the synthesis. This process is quite time consuming, so you'll have to wait until it completes the process, and then it will show you the waveforms as input and output waveforms basically. So black color window with green color is your complete waveform. There the option is zoom fit option. So if you'll click on the zoom fit option, and if you will maximize the waveform window, then you can easily see the possible combinations of inputs which you have provided, possible output which is there as an output of the program. So in this way, you can simulate any code and you can check the functionality of the code. This is a very basic steps. Industry is working in far more detail and depth, but right now we are working with the very basics. Even simulator also, we are using inbuilt simulator, which is there in the Vivado. We are not using model sim as a simulator, but we are using inbuilt simulator. Okay, so now we will start the synthesis process. Once we'll complete the synthesis process, then we will do the port mapping, and we will add the constraint file, and then we'll go for the downloading. For the synthesis, there is a green color triangle that is run synthesis option. Once you will click on that, it will map your code with the hardware which you have given. So right now, hardware which we have provided is artix 7. So this hardware, your code will get mapped in this hardware. So you can see on your right hand side, top right hand side, it is running synthesis design. That tab is continuously running. So once your synthesis get completed, there you will get the notification synthesis successfully completed. Now for the run implementation, instead of run implementation, make it cancel because we have not added any kind of constraint file here. To add the constraint file in the synthesis, go to the open synthesize design. If you will click on that triangle, then constraint wizard is there. Click on the constraint wizard. This will allow you to give the constraint to the program. Constraint of what? Constraint of inputs and outputs. So we are going to give the input and output pins through this constraint file. Now, for that, we will have a look on our kit first. So this is the kit. If you will see the kit, then there are very small on the kit, we are checking the pin number. Pin numbers can be given here. So for the switch, whatever is the number that we'll have to search and cite over there. This is the Digilant kit we have shown onto the video that we are using Digilant kit artix 7 board. Details of the kit we have already shown into the video. Right now we are simply giving the pin numbers. We are assigning pin numbers to the respective port. As two inputs are there, two switches we are connecting, two outputs are there, two output LED port we are giving to the output. Now where you can see the default LV CMOS is there, there you have to select LV CMOS 33. There you will have to select LV CMOS 33. Save this. If you will save, then constraint file will get generated. You will have to give the name of the file. Give any name to this file. This file will get saved with the extension .xdc. Your Verilog file, your test bench, both are having extension .v. That is Verilog. This is constraint file. It will get saved with extension .xdc. Once you save this, you can double click on that and check that file. Automatically pins has been written on in front of the respective port. This is the particular language. Even you can write this manually as well, but for simplicity, we have done through the GUI. If this particular GUI is not visible to you, you should check IO planning. If you will drag down this triangle, there is something which is called as default layout. There is something which is called as IO planning. For the constraint, we will refer to this IO planning wala layout. Now we will implement, we will generate the bit file. For the bit file generation, there is a one tab with run implementation. So first make the run implementation first, and then we'll go for the generate bit stream. So again, this will take some time. You can check your right hand side wala part to check the progress. If synthesis out of date message is there, then it will automatically get synthesized and it will automatically process your code. This will take some time. So have a patience. So in the video, if you observe carefully, constraint file plays an important role. Verilog file, first Verilog file is your module where you have written the code. Second file which we have added is test bench, and third we have generated constraint file. In the constraint file, port mapping is important. Usually for students, we do use LED, we do use switches, we do use LCD. So 3 to 4 peripherals would be sufficient. But if you want to go high-end applications, then you can, multiple ports are available on the board. You can explore, even Ethernet port is there, even USB compatible. This board is USB compatible. So you can save any kind of image on the USB and you can process on that image, and you can work on any image processing algorithm as well. Even few machine learning algorithm can also be implemented. So today's session is based on very basic, a very basic program, we can say, that is the half adder. Only input and outputs are 2 plus 2, that is 4. Now our implementation successfully completed. We will generate bit stream. So generate bit stream, make it okay. Once generating bit stream gets completed, after that, this is a kit which we have connected through the USB configuration to our system. So now we are going to do the downloading. So how we are going to do the downloading? For that, there is one option which is the Open Hardware Manager. On your left hand side downwards, there is something which is called as Open Hardware Manager. Just maximize it. Once you will open that Open Hardware Manager, Open Implemented Design will come, so you can make it okay or cancel, whatever. Open New Target. Now in front of you, Open Hardware Target is there. Go to Next. Go to Next. Before making this procedure, make sure your kit is on and it is connected to the USB. So your kit should be on. Okay, so go to Next. Select that particular kit. Go to Next on the screen. Make it finish. Once you will finish it, green side, there is something which is called as program device. So click on the program device. Select that device. These two files should automatically get a path. If one file is missing, it means your process has not completed properly. These two files will automatically get detected into the flow and then make program. Once you will program, you can see the output on the kit. So now program has been downloaded over here. You can see that 1, 1. Both inputs are 1 and 1. At that time, your output carry is 1 and sum is 0. If I'll change this, I'm changing now. See, for 1, 0, one input is 1, one input is 0. Your sum is 1, carry is 0. For both, if we'll make for both 0, your sum and carry both will be 0, 0. In this way, we have implemented the half wave, half adder onto the artix 7 kit. So this is the complete procedure through which you can implement your code on artix 7 using Vivado 2014 software. I hope you understood this program and the steps. So thank you very much for patience listening. Thank you.